Hi, this is Gordon Parker from Michigan Tech, and in this video I'm going to go through an introduction of system type. So to get started, let's take a look at a classic closed loop system architecture. Here I have transfer functions all over the place. D, G, L, those are all transfer functions in the Laplace domain. And I have two inputs, a reference input R and a disturbance input W. What system type allows us to do is in a very simple way, classify how the system responds in steady state to reference inputs and disturbance inputs. And it does it in a very compact manner by simply describing that in terms of integers. The thing that we're going to focus on is the polynomial order of the inputs. So now I have to switch to the time domain. For instance, if r of t was a step, and it looked like this is r of t, then this is a 0th order polynomial in time. Similarly, if w was a step, w would be a 0th order polynomial in time. Of course, in the Laplace domain, r of s would be 1 over s, a first order polynomial in the denominator in s. And we can keep going with this. If r of t was a ramp, like so, then this is a first order polynomial in time. And in the Laplace domain, it would be 1 over s squared. And we could just keep right on going. So we could have a parabola, for instance. Like so. And of course, that's second order in time. And in the Laplace domain, that's 2 over s cubed. So third order in s in the denominator. With that background, let's go ahead and define system type. We actually have two different versions of system type. We'll have type with respect to the reference input, R, and we'll also have type with respect to W, the disturbance input. Regardless of which one we're talking about, we can define it in the same basic way. Type is an integer. So that's kind of nice, very compact in terms of information. And it's the order of the polynomial input such that the steady state error, we'll just abbreviate that as ESS, such that the steady state error is a non-zero constant. So if I was given a system, a closed loop system, and someone said that this system is type 1 with respect to the reference input, I would then know, so maybe I'll write this as an example. If we had a system that was type 1 with respect to R, we then know that if I gave it a ramp, so R of t looked like that, then the steady state error would be some non-zero constant. So if I were to plot steady state error, or how about just the error, it might wiggle around a bit, but in steady state it would end up at a non-zero constant. Now, that seems like not a whole lot of information, but it's actually a ton of information. Because what it also tells us is what happens if we go to a lower order polynomial input and a higher order polynomial input. So there's actually much more information embedded in this concept. So let's revisit this example where we have something that is type 1 with respect to R. Again, we know that for a first order polynomial input, ramp, then the steady state error is going to be some non-zero constant. So if this is error, time, and there's R. What it also tells us, though, is that if we go down in polynomial order, so if I do a step, which is a 0th order polynomial, my steady state error is going to be 0. It might jump up, but eventually it'll be 0. So maybe I'll indicate here that the steady state error is not equal to 0 and constant. And it tells us something more. It also says that if we go up in the polynomial order, so in this case if I went to a parabola, my steady state error would be unbounded. So maybe it wiggles around and it goes off like so. So now my steady state error is unbounded. Running out of space, I'll abbreviate it like that. Now this example was system type with respect to the reference input, but it's the same idea for system type with respect to the disturbance input. If I had a type 0 disturbance input system, then I know that if I gave it a step input, I would have a constant steady state error. And if I gave it a ramp disturbance input, I would have unbounded error. Lots of information. So let's just summarize that using the variable q for system type. So if we're told that the system is type Q with respect to an input, either the reference or the disturbance, then if R of t is equal to t, to q minus 1, then the steady state error is 0. And if we have R of t is equal to tq plus 1, so one order higher, then the steady state error goes to infinity. And then of course the thing that our system type was defined as t to the q, it means that E steady state is a constant. And a special constant, that is, it's not equal to 0. Okay, so now let's go through the method of analysis. Here's the steps. The steps are the same for both system type with respect to the reference or the disturbance. You just have to do one little thing up front. If it's with respect to R, then what you do is you set R equal to 1 over s to the q plus 1. Remember, it's s to the q plus 1 because if I were to give it an input in the time domain, the polynomial order q, then in the Laplace domain, my denominator is going to be 1 higher than that. And we set w equal to 0. And if it's with respect to w, then we set r equal to 0 and w equal to 1 over s to the q plus 1. That's step 1. Step 2 is you form an expression for the steady state error. And of course this has to be a rational function. Simplify it out as much as you can. So a polynomial in the numerator and a polynomial in the denominator. Now you start off by setting q equal to 0. That's a step input. So we'll start there. And now you compute the steady state error. And finally, in the step 5 is if the steady state error is not equal to 0 and a constant, then the system type with respect to whatever input you're interested in is Q. Otherwise, or else, increment Q and go back to 4. And you just keep doing that until you eventually end up with the steady state error that satisfies this condition. Then you're good. So let's do an example. What I'll do is a extremely simple controller in a sense. It's just 1, where I normally had a D of S. And I'll put something in the feedback path, about a 1 over S. Plus plus, and a W. That's a plus right there. And there's our Y. Okay, so since we're going to be looking at system type with respect to both the reference input and the disturbance input, I might as well go ahead and develop both of those transfer functions. So for the reference input, if this is D, and this is G, and this is L, then I'll have dg over 1 plus dgl r. And for the disturbance input, I'll have G over 1 plus dgl times W. And now I can substitute in all these goodies and get actual transfer functions. So let's see, I'll have 3 over s squared plus 2s plus 2 over 1 plus 3 over s squared plus 2s plus 2. And that's times r. And then for this one, I actually get the exact same thing. That's interesting. This will actually point out an important feature of system type. So what we get is 3s over s cubed, actually. R plus the same quantity here. Now our gut instinct would be to say, well, since I have the same transfer functions for the reference input and the disturbance input, I might be inclined just to say, well, I'll do one of these system types, and then for, let's say, the reference input, and then just claim that the disturbance input system type is the same. That would be a big mistake. And I'll show you why right now. So let's first do the type with respect to R, the reference input. So what we'll do is we'll set R equal to 1 over s to the cube plus 1, and W equal to 0. So now Y is equal to 3s over s to the cube plus 1, s cubed plus 2s squared plus 2s plus 3. Now before I go off and do the steady state error, I have to remind myself what the steady state error is based off of, and that is this error function. And the error is always the reference input minus the output. So in this case, it'll be 1 over s to the cube plus 1 minus this value of y that we have directly above it. Before I can apply the final value theorem, I have to get e as a rational function. So my denominator is going to be s to the cube plus 1, s cubed plus 2s squared plus 2s plus 3. And in the numerator, I'm going to have s cubed plus 2s squared plus 2s plus 3 minus 3s. So that's e. And let me simplify that as much as I can. Doesn't look like I can simplify it too much, though. And I get this. And now we can go ahead and apply the final value theorem. So the final value theorem says that the steady state error is the limit as s goes to 0 of s times e of s. Of course, all the poles of s times e of s have to be in the left half plane. So let's go ahead and form that expression. S times e of s. Well, my numerator is actually going to stay the same. And what I can do with this s is cancel one of those s's there. So I'll get an s to the q, s cubed plus 2s squared plus 2s plus 3. And now I start marching along with that analysis approach, where I start off by setting q equal to 0. So let me rewrite this. S times e was equal to s cubed plus 2s squared minus s plus 3 over s to the q, s cubed plus 2s squared plus 2s plus 3. So I set q equal to 0. This term becomes 1, and then to get steady state error, I take the limit as s goes to 0 of s times e. I have s times e here, and I'll get 3 over 3, or 1. So I have a constant not equal to 0. So now I know that the type is 0. It's exactly what I have for q. So I now know that if I hit this system with a step input, reference input that is, I'll get a constant steady state error. And if I give it a ramp input, my error will grow without bound. Well, now let's do the other one. Let's do type with respect to the disturbance, w. So for that, I set w equal to 1 over s q plus 1, and set r equal to 0. So y is equal to 3s over s to the q plus 1, s cubed plus 2s squared plus 2s plus 3. And my error, which is always the reference minus the output, is actually equal just to the negative of this same expression. And I can simplify this, so I'll have negative 3 over s to the q, s cubed plus 2s squared plus 2s plus 3. And now I can go ahead and do my final value theorem work. So let's start with q equals 0. So my disturbance input is now a step. And the steady state error is equal to the limit as s goes to 0 of s times e. Well, if q equals 0, this goes away, and s times e then is equal to negative 3s over s cubed plus 2s squared plus 2s plus 3. And so that's 0. I have to keep going, so I'll increment q by 1 and go through this process again. Now, my steady state error is going to be the limit as s goes to 0 of negative 3s, but that s is going to cancel with this s, so it'll be negative 3 over s cubed plus 2s squared plus 2s plus 3. And so I get negative 1, a constant not equal to 0. So the type with respect to the disturbance, with respect to the disturbance w, is equal to 1. So let's go ahead and simulate this quickly and verify these results. Okay, so here's Simulink, and what we'll do is create this model. So So I'll grab a transfer function, and I'll grab another one for the feedback path, and I'll flip that one. Let's see, this transfer function is 3 over 1, 2, 2. And this one is just an integrator. Let me grab a summing junction. We'll need a couple of those. One there, one over here. I better stretch this out a bit. And I'm going to grab a couple of step inputs. And I think I'll grab some gains too, so that way I can turn my steps on and off. And let me move things over. Okay, so there's our reference input. Let's denote that as R. And we'll bring this feedback back here to like so. And better get the signs right, otherwise it'll be wildly unstable. I'll put this gain here. Right click, drag to copy that. Here's my disturbance input. And I actually have another transfer function in between here, but it's rather boring. It's just one, so I'll just bring that right into here. Now let's grab a scope, and we're just about ready to have some fun. So let's set up the configuration parameters with a fixed integration step size. I'll just use 100 Hertz. And we should be set. Oh, let me move a gain over to here too. And let's start off by just looking at the reference input. If I take a look at this step, the default value of it is that it starts at time equal 1 second and has a value of 1, so it's a unit step. And we'll run this. Ding. And there's the response. Now, it's still oscillating quite a bit, so let me go out for a little bit longer in time. How about 50 seconds? Now, we're putting a step into the reference input, and according to our analysis, this system should be type 0 with respect to the reference input. Now, what you see here is the output going to 0. Now, at first you might say, well, that looks good. Well, it's very bad, actually, because the reference input is a 1. So the steady state error is the difference between the reference input and the output. Let's go ahead and plot that out as a separate entity. So here's my reference. So what I'm going to do is create E. So there's my reference. Here's my output. I'm going to take R minus Y. So now this is E. And I'll go ahead and name this E. Now let's take a look at the error. Ugh. It goes to 1. Bad in the sense of if you wanted it to track a step, but it tells us exactly what we determined by looking at the system type. It's definitely a type 0 system. You give it a step input, you get a constant steady state error. Now let's look at the disturbance input. So I'll make this a 1. Now we know that the system type with respect to the disturbance input was 1. So if I put a step in here, I ought to see 0 steady state error. Let me move this gain to the other side of this, because I can see that when I grabbed my error signal, it didn't matter before, but it'll matter now. When I created my error signal, I was using the wrong side of R. Didn't matter because that was a 1, but now we're going to turn that into a 0. And this is a 1. That's good. And off we go. And our steady state error is 0, exactly what we would expect for a system that is type 1 with respect to the disturbance input, and we give it a step, a 0th order polynomial in the disturbance. So now let's go ahead and change that input to a ramp. And what we should expect to see is a constant non-zero error. So again, this is W, and off we go. And there's the error, down to -1. Exactly what we calculated with our steady state error analysis, and consistent with the fact that this is a type 1 system with respect to the disturbance input. So to summarize, we first looked at the definition of system type in terms of how it allows us to classify closed loop systems based on the polynomial input in both the reference and the disturbance. And the cool thing about system type is it's just an integer, but it tells us a lot of information about the system. And as we'll see in the next video, we can actually use it to help frame our control system design process. So again, this is Gordon Parker from Michigan Tech, and thanks for watching.